Now we are going to do the grand canonical ensemble, and grand canonical ensemble I will not do in great detail. So now the way this is constructed is the following. So we already said, and this is something you really should need to understand, and the best place to understand these things, I have tried to do a good job in explanation these things, but another person who has done a good job, though didn't have the figures and pictures, is the Terrell Hill. That's the second best place to look into other than my book. So now what we did in doing the canonical partition function, we put the large number of systems characterized by NVT, but each of them have different energy levels, because energy is not conserved, not constant in NVT. We put them together in contact with each other, and then we put it in a bath, and we let the temperature go to constant T. When the temperature is equilibrated, we take it out, and then we put an insulation around this system. So that becomes, with this large number of systems, so the microcanonical ensemble becomes a whole microcanonical ensemble becomes a super system in a canonical ensemble. Now I put a canonical ensemble by making, so my insulated system is now forms a system of my microcanonical. The whole idea of going back from canonical to microcanonical is that I can use the principles of microcanonical ensemble, which is essentially S equal to Kb ln omega. But now, because of my construction of super ensemble and super system, I am now handicapped with two constraints. One is the total number of systems that constitute my ensemble is Ns, total Ns, then and the energy is also conserved. So I need to go to conservation of energy, because I need to go back to microcanonical ensemble. If I do not go to microcanonical ensemble, I cannot use S equal to Kb ln omega. So I go that, and then I put omega, the way to distribute. Now each system has a different energy, so I distribute. But so Nj is the index, Nj is the number of systems in energy level J. So it's a different, Nj is not what you have usual thing. So it is this whole system that we are considering, and the system has the energy level Ej. So Nj, so with that the constraint and the combinatorics, the multinomial expression of the total omega, we go on and did the calculations, going back and forth between microcanonical ensemble and the canonical, and we derived all that we derived, and it's a formidable exercise. Next level, then now I want to so I have allowed energy to fluctuate in lieu of the intensive variable temperature. Now I am going to let total number of particles fluctuate, because that is very important in many applications. The total number of particles, like you are undergoing a chemical transformations or phase transition, total number of particles not conserved. Like you have a gas liquid at equilibrium, then the molecules are exchanged between the two phases. That is, so when we allow that, the next level I allow the fluctuation of number or change of number, then that is the grand canonical ensemble. And so we do again the same thing. We put my grand canonical things, and we now replace the wall, like in a canonical we let the system interact energetically. So the walls are porous to exchange energy, but not number. Now I make the walls porous that number of particles can also exchange. Then I take all these porous system, put them together, put it in a kind of chemical potential bath, so that I ensure by particles come in, whatever particle want to come in, come back, they equilibrate. In addition, I have the thermal bath, so the system has now constant energy, constant chemical potential and constant temperature, and the huge number of that. So, from grand canonical, I first go to canonical, then from canonical I go to macrocanonical. So, before I had one step, now I have two-step process, and then I play the same game that I played, which is I had two constant, now I have three constant, because not only the total number, I also have energy, and as a result of that, I will now have three undetermined multipliers. One of them again becomes alpha, one is beta, and is gamma. And the form that comes in at the end of the day, I have, instead of having one sum, which is sum over G levels, I also have, because each system has different number of particles. So, I have sum over n, and this is the conservation condition that comes in. I am not going to do through the whole thing, but it just parallels the whole thing that I am not going to do. So, now in addition to having, so now I have the following double probability. Probability that my system in energy level Ej. So, J is the index for the energy of the system, and N is the index for the number of particles in the system. So, Pj is now defined by Nj by N, which is the normalization. So, if this condition is my probability, bare probability, then I have to normalize it by summing over all these things, and this comes from the undetermined multiplier. So, probability a system has n number of particles and in energy level J is now given by things e to the power minus gamma n, and beta is 1 over kBt. Then one undergoes through another exercise and the derivation. At the end of the day, one shows that this e to the power minus gamma, you know what is the quantity e to the power minus gamma? So, what happens that, so e to the power gamma n, so this becomes, one is the chemical potential, another becomes fugacity. So, e to the power minus gamma, that becomes Z fugacity, but I can also write gamma is the chemical potential, as you correctly said. So, beta is 1 over kBt, and this is the chemical potential, though I usually like mu, but I think one has followed the notation of Macquarie here. So, this is the probability distribution, and this is the grand canonical partition function. Then one does the realize here that I take, so let me write down that, since this is the kind of repetition, same thing we did in. So, okay, there are many possible notations of this grand canonical partition function. Okay, I have used this one. The reason is that Z is taken away. I will explain to why Z is, capital Z is taken away. So, this is now number of energy levels, then this e to the power minus beta Ej e to the power minus gamma n. Z usually is put in e to the power minus gamma, which is this fugacity, this is the chemical potential, then this is now this Ej. So, I can take this sum out, I can take this sum in J, I can do beta Ej. So, this is the energy of a system at a characterized by N and V. So, this is then is the canonical partition function. So, this thing is now is really very nice. So, this is the definition of the grand canonical partition function. You know, I do not want to go through the detail because it is more elaborate, but essentially repetition of what we did, and it just will bore you and will rob you of the beauty of the whole thing. But this expression is just beautiful. This is a notation I always use, and now one can play the same game again, same thermodynamics that we played before, by going over all the way back and forth. Again you have to write the entropy, but now the entropy you will write as entropy is Pj ln Pj, which is now a function of also of n, okay, and same thing you will do, and then you come to this beautiful relation that in grand canonical ensemble. So, we call this term KBTLN is the thermodynamic potential. So, let me write down all three, you will see the beautiful symmetry, and I mentioned before that all these things was just done by one person. So, S equal to KB A actually many people say okay, we will put it like that. So, this is microcanonical, this is canonical, and this is grand canonical. And everywhere you have to get the extremum of the quantity. So, on the left hand side that I have written is the quantity that has to be maximized. Why? Because partition the system is something quite remarkable, but that is that you have to find the macroscopic state of the system. And so, macroscopic state of the system many times, so when we try to say the crystal transition, say going to iron going to FCC lattice from the melt, then what do? You have to find out which state is more stable, or you want to understand nucleation, the formation of the critical droplet, or you want to do osmosis, or all these phenomena that we study which are equilibrium, we treat them as equilibrium phenomena. Nucleation is a dynamic part, but we will do that later. In that case, you have to find out, okay, so when I decrease the temperature and melt will go to a crystal or liquid will go to a crystal, that has to be selected. How is it selected? I go and maximize the thermodynamic potential, and that principle of maximum will bring out that state which is given by the density or other order parameter or characteristics function. This calculation will show that how it will select, because if I plot the free energy, then free energy against, let just be very simple, gas liquid, so density, then at a coexistence they have the same free energy. But when I go below, so this is liquid, this is gas, but when I go to lower temperature, because temperature is the control parameter, then this becomes like that. So, when I now do my statistical mechanics and calculate the free energy and minimize the free energy or maximize thermodynamic potential, if I am in grand canonical, then I have to maximize PV, okay. Then I will see this thing will, that maximum PV will give you a solution which is, will give the low temperature will be the liquid state, okay. So, it is a principle of extremum that controls the thermodynamics And that is what we call the free energy has to be minimum, which essentially we are saying that state will be selected which has the maximum partition function. And yes, sure.
So if you calculate pressure in this canonical partition function and if you calculate the pressure on the canonical partition, both
this is extremely good question. I should talk about it tomorrow. So that is the answer to this question will be answered in or it will be answered in many different ways. One of them is that when you go to grand canonical partition function, you are allowing number fluctuation. What can be shown that this number fluctuation is decreases when n goes to infinity. So that is a very strong theorem, essentially comes from probability theory, that in the limit of infinite system, predictions of all three becomes the same. For example, if you try to do gas liquid equilibrium even in computer simulation in a canonical ensemble, you will never see the flat isotherm. You always see a Maxwell loop, which is unrealistic. Maxwell corrected it. That because the fluctuations that are necessary are not captured in the canonical ensemble, the number fluctuations. So, you can of course get rid of the loop if you go to the limit of infinite system. And you can see by increasing system size that artificial loop goes down because fluctuations are coming in. So, the answer to your question that as we go to infinite system size limit, all the systems microcanonical, canonical, grand canonical, and there is one little bit we will dwell on tomorrow is isothermal isobaric ensemble, then there is a Gibbs ensemble, all these ensembles. They all become, the grand canonical is still mu Vt, we still have to replace the extensive variable, one is remaining the V, that has to be replaced by P. When you do mu Pt, that is the Gibbs ensemble. And isothermal isobaric is NPT. So, there are two more ensembles that people use. So, NPT is the one which is most of the time computer simulation people use. Okay. And however, the thermodynamic potential which is so uniquely comes out in these three partition functions do not come there, but there are ways to think about it. So, answer to your question, when in the limit of infinite system size, all the ensembles give identical result, and that can be proven. That is a mathematical statement. But this is really formidable and beautiful construction that Gibbs did, sitting quietly alone, is one of the most powerful theoretical framework that we use. Anything else? In molecular dynamics in grand canonical, I have not known, people must have done, but I do not know what kind of, see how does molecular dynamics simulation go? Molecular dynamics go through introducing thermostat, introducing barostat. Barostat takes care of the pressure, thermostat takes care of the temperature. So, these are the kind of coupling to the bath you introduce. Remember, how do you introduce thermostat? Whenever velocity of a one particle, when the temperature goes up, you scale the velocity of every particle, very artificial way. And when temperature goes down, you upscale the velocity of every particle. This is called Verlet scaling. Now, if you come to pressure, similarly, whenever fluctuation pressure becomes less, you barostat, you lower the volume, and when the pressure becomes large, you release the volume. That is the allowing volume fluctuations. That is how your pressure barostat works. Okay, just like piston, just like piston. So, now you have to think of how to get the number of particles. So, you need Another like thermostat, barostat, God knows one number stat. So, number stat will allow you to increase the fluctuation. Now, if I am doing a simulation in a grand canonical ensemble where number of particles can leave the system, then you have to use a reservoir rule. Now, thermostat we use Varley rule and some other rules. Pressure we use Berenson and Nose-Hoover. There must be have been done, but I don't know that in grand canonical what is happening when you do barostat or you do Nose-Hoover. There are certain rules coming from conservation which allows you to write an equation. So, you need to write an equation that your pressure goes up, then that there is a systematic way to bring it back down. Similarly, thermostat, there is a systematic way to bring the temperature back. You know, it is not heuristic. It has to obey certain rules. Those rules or equations, whether they have been done for grand canonical ensemble, certainly it has done, but it's certainly not a popular way. I have never in my entire life used molecular dynamics in grand canonical. It's because I think we do canonical, then isothermal, isobaric and microcanonical. I have not seen, but you can do the literature search if anybody has done.